Hey everybody, and welcome to the second of a couple of videos on the interrelation between our three interpretations of probability. Probability as rational belief, as relative frequency, and as chance. In the last video, we saw how if we assign chances to objects or events having a given property, we can, in the presence of some independence assumptions, use that information to very readily compute the chance that the relative frequency of the given property within a fixed reference class takes on a certain value. We also highlighted an implication of the law of large numbers that laid down a very tight connection between chance and limiting relative frequency. As the size of the considered reference class grows, the chance of the relative frequency being very close to the objective single-case chance gets very close to 1. Relative frequencies converge to chances in the long run, given our assumptions like the existence of uniform and independent chances. Now let's bring rational belief into this picture. To do so, let's consider an example. Again, we'll use a coin example because these are particularly simple and illustrative. Example. So suppose we're flipping a coin that's of unknown bias, and we think there are two possible chances, right? Let's say 1/3 towards heads and 2/3 towards heads. So we'll say maybe H1 will let be the hypothesis or the proposition that the bias toward heads of our coin is 1/3, and we'll let H2 be the hypothesis that the bias toward heads is 2/3. Okay? Now, suppose that we think H1 and H2 are equally likely. So this is our epistemic probabilities, or our rational beliefs now. So suppose that I'll use P to represent my epistemic probabilities. Suppose I think the probability of H1 is equal to the probability of H2 is equal to 1/2. Right? Each of these chance hypotheses are judged equally likely by me. Now perhaps someone else starts flipping the coin, and they report to me the relative frequency of heads in their series of flips, as well as the size of the series of flips. So let's let H here be the property of a toss landing heads, right? And we'll say D, big D is the reference class, so maybe X1 through Xn, where these little X's represent the different tosses of the coin. So toss 1 all the way through toss N. I want to know, suppose that I know the size of the reference class, that it has n members to it, and suppose someone reports to me the relative frequency in that reference class of heads, right? Let's say they say it's equal to, let's make this concrete. So we'll say in our example, for example, we'll say D has 3 tosses in it, right? X1, X2, and X3. So that someone tosses the coin 3 times, and I know that. And then they report to me that the relative frequency of heads is 2/3. So 2 of those 3 tosses landed heads. Now we might ask, given this information, what should be my new epistemic probability in the chance hypotheses? So for example, what should be my new probability that the coin is biased 1/3 towards heads? Right? We know what my old probability was. It was just 1/2, right? But now, I've learned that the relative frequency in these 3 tosses that we've had of heads is 2/3. So let's suppose that I update by conditionalization. Well, if I update by conditionalization, that means that my new probability has to be equal to the old probability, which we were just calling P, of that proposition of interest, in this case, that the bias of the coin is 1/3 towards heads, given the evidence that I just learned, which is that the relative frequency of heads in this sample of size 3 was 2/3. Okay? So this is what I have learned. Now, this should give me my new probability, right? My new probability in H1 is equal to my old probability of H1 conditional on what I just learned. So we can use Bayes' theorem, to try to figure this out. Because this is a case where we're trying to figure out a conditional probability, and it's not immediately apparent what it is, but it would be easier to figure out what the reverse conditional probability is. So by Bayes' theorem, this is really equal to probability of the relative frequency of heads being equal to 2/3, given that the coin is biased 1/3 towards heads, times the probability, the prior probability that the coin is biased 1/3 towards heads, all over, right, the same thing again. Probably would get that relative frequency given h1 times the probability of h1. Now we consider, right, the other hypothesis, right, what's the probability we would get that evidence, get that relative frequency, even given, right, the other alternative hypothesis, h2, right, times the probability of h2. Okay. Now let's see if we can compute this out. So these h1 and h2s are chance hypotheses, right? So they specify the chance that the coin is going to land heads on any particular toss, right? h1 says it's 1/3, h2 says it's 2/3. So we can use the same sort of method we talked about in the last video to figure out what those conditional probabilities are. So why don't I actually do a little aside here and highlight that for us so we remember how to do that. Okay, and we'll actually make it a little more explicit and formal than we did even in the last video, right? So given that we know the size of the reference class here, when we're asking what's the probability we'd get a particular relative frequency, what we could see that as asking, right, what's the probability that k objects would have a particular property, let's say property x out of, right, n total objects, right? So what's the probability that if we have n objects, k of them will have a particular property x, right? Now, if we assume that each individual object has the same chance of having the property x, right? Then, and let's write that, how about we write the chance of, and let's say the ith member of our reference class having the property x is equal to the chance that the jth member would have property x, all I and j. And let's say it's equal to some, right, fixed number r. R is then the chance that any individual object in our reference class out of these n total objects has the property x, right? So what's the probability that k objects have property x out of those n total objects? Well, right, given an independence assumption about the chances, we can multiply through here, and we can take the chance that they'd have x, right? We need to have that happen a total of k times. So we need to take r to the k times, we need to have n minus k things that don't have property x, right? And the chance of not having property x is going to be 1 minus r. So we get 1 minus r to the n minus k, right? Now that's the probability that you get a particular sequence of our n objects with k of them having the property x and n minus k of them not having the property x. But we have to take into account that there's a bunch of different sequences that could have that property, that could involve k objects having property x and n minus k not having property x. So we really have to add up all those different possibilities together, right? And mathematically what that ends up amounting to is multiplying this whole chance right here by n choose k, right? Which is, right, the number of ways of selecting k objects out of n total objects, right? Here, right, I'll write to the side that n choose k is equal to n factorial over k factorial times n minus k factorial. Okay, where factorial, right, I'll say n factorial, that's just equal to n times n minus 1 times n minus 2, so on down to 1. Right, so for example, right, 4 factorial would be equal to 4 times 3 times 2 times 1. Okay? All right. So this gives us a handy formula then for computing, right? Once we know how big our reference class is, how many objects we're looking at, it gives us a handy formula for computing the chance that we would get a particular relative frequency of a property within that reference class, given the assumption, right, that of course we have these uniform independent chances. Okay, and that's what we have in this coin example. So now let's go back here, right? We're here interested, right, in this P function, right, which is epistemic probability. But the principle, remember, connects epistemic probability with objective chance, right? So since these H1 and H2 propositions are chance propositions, our epistemic probabilities for these relative frequencies conditional on the H1 and H2 are just going to be the chances that we would get those particular relative frequencies. So let's first think about this first part here, right here, right? The probability that we would see that relative frequency given H1. Well, what's the probability that we'd see a relative frequency of 2/3 heads within our 3 tosses? Well, right, it would be the chance that we would get heads on any particular toss, right? And we need to get heads happening twice, so it would have to be, according to hypothesis H1, right, a 1/3 chance we'd get heads times a 1/3 chance we'd get heads again times a 2/3 chance that we'd get tails. Now we have to consider, right, that this could happen 3 different ways, right? Which really in our formula from before, right, is, let's see, n here is 3, choose 2, right? 3 tosses, choose 2 of them to be heads, which is just 3, right? Okay, so this is the probability that we would see that relative frequency given the H1 hypothesis. Now we have to weight that by the prior probability of the H1 hypothesis, which we said was 1/2, started out as 1/2. And we divide all that by the same thing on the bottom, 1/3 times 1/3 times 2/3 times 3 choose 2 times 1/2 plus, okay, now what's the probability we'd see that relative frequency given the H2 hypothesis? Well, right, there we're going to have a 2/3 chance of getting heads times 2/3 chance of getting another heads times 1/3 chance of getting another tails, right? Since under the H2 hypothesis, there's only 1/3 chance of tails. But again, we have to consider, right, that this could happen in 3 choose 2 different ways, right? And then we weight that all by the prior probability of H2, which again is just 1/2. Okay, now we can solve all this out, it's just a matter of calculation. This whole thing then equals 1/9 over 3/9, which is equal to 1/3. Okay, so our new probability in the H1 hypothesis becomes 1/3, which means we have 2/3 probability in the H2 hypothesis. And this is what we'd expect to see, right? Since we've now seen, right, 2/3, we've seen more heads than tails, right? So we'd expect that to support the hypothesis that the coin is biased towards heads rather than tails, which is the H2 hypothesis. Okay, so now if we employ conditionalization and Bayes' rule, right, by learning relative frequencies, I end up with updated epistemic probabilities about chances, right? So this ties the 3 kinds of probabilities we've been looking at together, right? We could sum this up by saying, if we will, that relative frequencies supply evidence for my beliefs about chances. Right? So they supply evidence that underwrites my beliefs about chances. And there we have all 3 kinds of probability showing up. Right? Now, just as we had a tight result connecting chance and relative frequency in the limit or in the long run, there's a similar sort of result that again we won't prove, just like we didn't prove the results about chance and limiting relative frequency, because it involves a little bit more mathematics than we want to go into. But we can state it informally, right? And basically the idea is that as the size of the data set, which supplies our information about relative frequency, grows, then our degree of beliefs will converge to true chances, right? So in this coin case, for example, if the true chance really is either 1/3 or 2/3 in favor of heads, then as we get more and more data, as we flip the coin more and learn more and more about the relative frequencies of those larger data sets, of heads within those larger data sets, and we update by conditionalization on that new information, then our degree of belief in the true chance, which is recall is either 1/3 or 2/3, will get very close to 1, right? And hence that means that our degree of belief that the coin will land heads next time will also get very close to matching the true chance, right, that it actually will land heads next time, right? So we have then, right, what we might want to call convergence to the truth, right? Which says informally, right, that in the long run, right, relative frequency information, leads epistemic probabilities to concentrate around true chances. With very high chance, right? That is very high objective chance, right? We could also state this in terms of epistemic probability too, though, right? It will also lead this to happen with very high epistemic probability, with very high true chance, right? Assuming, right, there's an assumption here, in addition to, of course, the assumptions that there are true chances and they're independent and all this. There's also an assumption here that our epistemic probability in the true chance hypothesis is greater than 0, right? So because if it started out as 0, then no matter how much we conditionalize, we would never increase its probability. So the assumption is that the probability of x is greater than 0 if x is the true chance hypothesis. True chance hypothesis. Okay. Now, right, we then have that rational agents are going to tend to believe that their degrees of belief will concentrate around true chances in the limit when we have all these assumptions and setup in play. This then justifies also an agreement theorem, right? Agents with different prior probabilities about chances will tend to converge toward the same degrees of belief in the limit, provided they all assign positive probability to the true chances. So we could draw a simple graph to help us illustrate this. Along the x-axis, we could have time, and along the y-axis, we could have my belief in the true chance. Right, so let's say there's some true chance to the coin landing heads. Maybe it is, right, I don't know, 1/2 is the true chance. Right? This, right, I can think maybe my initial degree of belief in that chance, the true chance, is 0.2. So I've only assigned 0.2 epistemic probability to the chance of the coin landing heads being 1/2, maybe at the start. But what these convergence results tell us is that over time, right, no matter where I start, I'll converge up to 1, right? I'll go to degree of belief 1 in the true chance, no matter where I am, right? If I started up here, right, I'll start down here. So you could have then different people who start out with very different prior beliefs about the relative likelihood of the true chance hypothesis, but they'll all, in the limit, converge to assigning near probability 1 to that true chance hypothesis. So because they converge to the truth, they're also converging close to each other. Okay, so then we then have that, right, agents with different prior probabilities about chances will tend to converge toward the same degrees of belief in the limit, provided they all assign positive probabilities to the true chances, right? So there are then tight connections, at least in the long run, between rational degree of belief, relative frequency, and chance. And hopefully this video has helped us see some of those tight connections. Please remember to complete the participation poll for this video, and I'll see you guys next time. Thanks.